The morning of August 14th, 1945, broke gray and humid over Iwo Jima's volcanic ash. First Lieutenant Urban Drew of the 413th Fighter Squadron pulled his leather flight jacket tight as he walked toward his Republic P-47N Thunderbolt. The aircraft sat massive and imposing on the coral-dusted hardstand, its yellow trimmed tail gleaming in the Pacific dawn. At nearly 20,000 pounds fully loaded, the P-47N represented something unprecedented in aviation history, a single-engine fighter that could fly farther than most twin-engine bombers. Drew paused beside the enormous radial engine cowling, running his hand along the gun ports that housed 8 50-caliber machine guns. Each weapon carried between 350 and 450 rounds of ammunition, enough firepower to shred a Japanese destroyer. But it wasn't the guns that made this particular Thunderbolt revolutionary. It was what Republic Aviation's engineers had hidden inside those massive wings. 93 gallons of aviation fuel in each wing, transforming this fighter into something the Japanese had never encountered before. "Detroit Miss 2, Drew murmured, reading the name painted beneath his cockpit. The aircraft's serial number, 44-88492, was stenciled in regulation white letters. This particular P-47N had rolled off Republic Aviation's production line in Farmingdale, New York, just months earlier, one of 1,816 P-47NS that would be built before production ended. Drew had no way of knowing that this August morning would mark the final full day of fighting in World War II. 2,350 miles. That was the theoretical maximum range of the P-47N, when carrying its full fuel load of 1,266 gallons. No single-engine fighter in history had achieved such range. The closest competitor, North American's P-51D Mustang, could manage approximately 1,600 miles under optimal conditions. But the P-47N could fly from Saipan to the Japanese mainland, conduct combat operations, and return, a capability that transformed the strategic bombing campaign in the Pacific. The development of this long-range capability had begun in the summer of 1944, when Republic Aviation's chief engineer Alexander Kartveli faced an impossible challenge. The war in the Pacific demanded fighter ranges that exceeded anything achieved in Europe. Bomber formations flying from newly captured islands in the Marianas needed escort fighters capable of protecting them during flights that could last 8 to 10 hours. The existing P-47D, with its maximum range of 820 miles, simply couldn't make the journey. Kartveli's solution was elegantly simple and technically revolutionary. He took the third prototype YP-47M, serial number 42-27387, and fitted it with an entirely new wing design. This wing, 18 inches longer than the standard P-47D wing, incorporated internal fuel tanks for the first time in Thunderbolt history. The wing root was expanded by 18 inches, while the wingtips were clipped by 6 inches, creating the distinctive squared-off appearance that would characterize all P-47NS. But the fuel capacity was only part of the equation. The P-47N's Pratt & Whitney R2877 double WASP engine produced 2,800 horsepower, driving a 4-bladed Curtiss electric propeller through a General Electric CH-5 turbo supercharger. This power plant combination gave the aircraft a maximum speed of 467 miles per hour at 32,000 feet, while maintaining the high-altitude performance that made the Thunderbolt series so effective. By September 1944, the first production P-47N-1 RE aircraft were rolling off the assembly line at Republic's Farmingdale facility. The transformation of the factory to accommodate P-47N production had required significant modifications. New jigs and fixtures were installed to handle the longer wings, while additional fuel system testing equipment was brought online to verify the integrity of the wing-mounted fuel cells. The human cost of this production effort was enormous. At the Farmingdale plant, 9,087 P-47 Thunderbolts of all variants were manufactured between 1941 and 1945. The workforce, which had expanded from a few hundred employees to over 25,000 at peak production, included a significant percentage of women workers who had entered the aviation industry for the first time during the war. Rosemary Chun, a riveter on the P-47N wing assembly line, remembered the precision required for the fuel tank installation. "Every rivet had to be perfect," she recalled years later. "We knew these planes were going to fly missions longer than any fighter had ever flown. A fuel leak over the Pacific Ocean meant certain death for the pilot. We took that responsibility seriously." Chun, whose husband served in the Pacific with the 7th Fleet, worked 12-hour shifts 6 days a week throughout 1945. The technical challenges of the P-47N extended beyond fuel capacity. The aircraft's gross weight of 19,880 pounds required strengthening of the landing gear, which increased weight and complexity. The larger wings, while providing additional fuel storage, also changed the aircraft's flight characteristics. Test pilots at Republic reported that the P-47N had improved roll rate due to the larger ailerons, but the additional weight required careful attention to center of gravity calculations when loading external fuel tanks. Captain James Morrison, a test pilot at Republic's Farmingdale facility, conducted many of the early P-47N evaluation flights. "The airplane was a brute," Morrison recalled, "but it was a predictable brute. The controls were heavy, especially in pitch, but the aircraft would do exactly what you asked it to do. The fuel system was the most complex we'd ever installed in a single-engine fighter. We had fuel pumps, transfer pumps, and selector valves that had to work perfectly for 8 or 10 hours at a time." Morrison's test reports, filed with the Army Air Forces Technical Command, documented the P-47N's performance across its entire flight envelope. At 25,000 feet, carrying full internal fuel and 2 165-gallon drop tanks, the aircraft could cruise at 270 miles per hour while consuming approximately 130 gallons of fuel per hour. This gave the P-47N a theoretical endurance of nearly 10 hours, longer than any single-engine fighter then in service. The first operational P-47N squadron was the 318th Fighter Group, commanded by Colonel William Looney. The group had been flying P-47D aircraft from Saipan since June 1944, supporting the amphibious assaults on Guam and Tinian. When the first P-47NS arrived via Escort carrier in March 1945, Looney immediately recognized their potential. "We could finally escort the B-29s all the way to Japan," Looney wrote in his post-war memoir. "For months, we'd been limited to relatively short-range missions in the Marianas. The bombers were flying unescorted deep into Japanese airspace, taking heavy losses to fighter interceptors. The P-47N changed everything. The 318th Fighter Group's conversion to the P-47N was not without challenges. The aircraft's increased complexity required additional maintenance training for ground crews, while pilots had to adapt to the different handling characteristics of the longer-winged fighter. The group's operations officer, Major Robert Hayes, established a rigorous training program that included long-range navigation exercises and emergency procedures specific to extended over-water flying. One of the most significant challenges was fuel management. The P-47N's fuel system included internal tanks in the fuselage and wings, plus provision for up to 4 external drop tanks. Pilots had to master a complex sequence of fuel transfers to maintain proper center of gravity while maximizing range. A mistake in fuel management could result in an aircraft becoming uncontrollable or running out of fuel hundreds of miles from the nearest friendly airfield. Lieutenant Colonel Francis Gabreski, the leading American ace in the European theater with 28 confirmed victories, had the opportunity to fly the P-47N during a visit to the Pacific in May 1945. His assessment was characteristically direct. "It's a different airplane entirely from the D model. The range is incredible, but you pay for it in handling. This is an airplane for experienced pilots who understand energy management and fuel planning." The Japanese response to the P-47N was immediate and concerned. Intelligence reports captured after the war revealed that Japanese air defense commanders quickly recognized the threat posed by the long-range American fighters. Colonel Saburo Shindo, commanding officer of the Japanese Army Air Force's 3rd Air Army, issued a tactical bulletin in April 1945 warning his pilots about the new American fighter. "The enemy has deployed a new variant of the P-47 with greatly extended range," Shindo's bulletin stated. "These aircraft can escort bombers to any target in the homeland and remain on station for extended combat. Our pilots must avoid prolonged engagement with these fighters, as they carry more ammunition and fuel than previous variants. Major Yasuo Kuwahara, a veteran Japanese pilot with the 244th Sentai, encountered P-47NS during the massive Allied air raids of May 1945. "We knew immediately when we faced the new Thunderbolts," Kuwahara recalled. "They stayed with the bombers throughout the entire mission, something the earlier American fighters could not do. Our tactics of waiting for the escorts to turn back for fuel no longer worked." The P-47N's combat debut came during the Battle of Okinawa, when aircraft from the 318th Fighter Group flew fighter sweeps over the Japanese home islands to intercept kamikaze formations before they could reach Allied shipping. On May 25, 1945, 16 P-47NS led by Major John Smith intercepted a formation of 24 Japanese aircraft over Kyushu. The engagement lasted 45 minutes, with the P-47NS using their superior firepower and fuel capacity to maintain continuous pressure on the Japanese formation. Smith's after-action report documented the destruction of 11 Japanese aircraft, including 6 Nakajima Ki-84 Frank fighters and 5 Mitsubishi A6M-0 fighters. No P-47NS were lost in the engagement. "The Japs couldn't believe we were still there after an hour of combat," Smith reported. "They kept disengaging, expecting us to turn back for fuel. When we stayed on their tails, they started making desperate moves that just made them easier targets." This engagement demonstrated the strategic impact of the P-47N's extended range. For the first time in the Pacific War, American fighters could maintain air superiority over the Japanese home islands for extended periods, disrupting kamikaze operations and providing protection for the strategic bombing campaign. The production of P-47NS required coordination between Republic's Farmingdale facility and the company's secondary plant in Evansville, Indiana. The Evansville factory, which had been constructed specifically to meet wartime P-47 production requirements, produced 149 P-47N aircraft between December 1944 and the end of the war. The plant employed over 10,000 workers at peak production, including significant numbers of women and minorities who had entered the aerospace workforce for the first time. Martha Rodriguez, a quality control inspector at the Evansville plant, was responsible for checking fuel system installations in P-47N wings. "Every connection had to be perfect," Rodriguez recalled. "We were dealing with high-octane aviation fuel under pressure, flying at altitudes where the smallest leak could cause catastrophic failure. I rejected dozens of wings that didn't meet our standards, even though it meant production delays. The quality control standards at both Republic facilities were extraordinarily high. Each P-47N underwent extensive ground testing before its first flight, including fuel system pressure tests, engine run-ups, and avionics checks. The aircraft was then flown by Republic test pilots through a comprehensive evaluation program that included high-altitude performance tests, fuel consumption measurements, and handling evaluations across the entire flight envelope. These quality control measures were essential given the P-47N's operational requirements. Unlike fighters operating in Europe, where emergency landing fields were relatively common, P-47NS flying Pacific missions faced thousands of miles of open ocean between friendly bases. Mechanical failure over the Pacific meant almost certain death for the pilot unless the aircraft could reach one of the few emergency landing strips on isolated islands. The 413th Fighter Group, commanded by Colonel Marion Carl, received its first P-47NS in May 1945. Carl, a Marine Corps ace who had transferred to Army Air Forces Command for the P-47N program, immediately began planning extended-range missions against Japanese targets. The group was stationed on Iwo Jima, a small island captured during the Okinawa campaign, which provided a forward base for long-range operations. Carl's pilots included some of the most experienced fighter pilots in the Pacific theater. Captain Robert Anderson had 23 confirmed victories flying P-38 Lightning aircraft in the Southwest Pacific. Lieutenant William Chun had transitioned from P-51 Mustangs, bringing extensive experience in long-range escort missions. First Lieutenant Joseph Martinez had flown P-47D aircraft with the 318th Fighter Group and was one of the first pilots to master the P-47N's complex fuel management systems. The group's first extended-range mission was flown on June 15, 1945, against aircraft factories in the Nagoya area. 16 P-47NS, each carrying full internal fuel and two 165-gallon drop tanks, departed Iwo Jima at 0600 hours. The flight plan called for a cruise to Japan at 25,000 feet, combat operations over the target area, and return to base. A total mission time of 8 hours and 40 minutes. Captain Anderson led the second flight of 4 aircraft. The fuel management was critical, Anderson recalled. We had to transfer fuel from the drop tanks in a specific sequence to maintain center of gravity. Too far aft and the aircraft became uncontrollable. Too far forward, and you couldn't trim the nose down for cruise flight. We practiced these procedures for weeks before the first combat mission. The mission profile required precise navigation and fuel planning. The P-47NS would cruise outbound at economical power settings, conserve fuel during the transit to Japan, and then have sufficient fuel remaining for 30 minutes of combat plus reserves for the return flight. Any deviation from the planned fuel consumption rates could leave aircraft stranded over the Pacific Ocean. Weather over Japan on June 15th was marginal, with cloud cover at 15,000 feet and visibility reduced by industrial haze. The P-47N formation maintained radio silence during the approach, relying on celestial navigation and dead reckoning to reach the target area. At the initial point, the formation split into 4 aircraft elements to attack separate targets within the Nagoya Industrial Complex. Anderson's element targeted the Mitsubishi aircraft engine plant, where Japanese workers were producing radial engines for fighter aircraft. The attack began with a high-speed diving pass from 28,000 feet, with the P-47NS reaching speeds exceeding 500 miles per hour in the dive. Each aircraft carried 3,000 rounds of .50 caliber ammunition, allowing for sustained firing during multiple attack passes. The target was heavily defended, Anderson reported. We counted at least 40 anti-aircraft guns of various calibers, plus searchlights and smoke generators. The Japs had learned to put up a wall of flak that you had to fly through to reach the target. The P-47N's rugged construction was essential for surviving that kind of defensive fire. The Mitsubishi engine plant sustained severe damage during the attack. Post-war assessment revealed that the P-47N strikes destroyed approximately 60% of the facility's production machinery and killed over 300 Japanese workers and technicians. Engine production at the plant never returned to pre-attack levels, contributing to the critical shortage of power plants for Japanese aircraft during the final months of the war. The return flight from Japan tested the P-47N's endurance capabilities to their limits. Several aircraft experienced fuel system problems that required emergency procedures to transfer fuel from wing tanks to the main fuselage tank. Lieutenant Chen's aircraft developed a fuel pump failure that left him with reduced fuel flow, forcing him to operate at minimum power settings for the final 200 miles to Iwo Jima. I was calculating fuel consumption every 15 minutes, Chun recalled. The engine was running so lean that it was barely developing enough power to maintain altitude. I had to descend gradually and accept a lower cruise speed to stretch the remaining fuel. When I landed at Iwo Jima, the fuel gauges were reading empty. Despite these challenges, all 16 P-47NS returned safely from the mission. The success of this first long-range strike validated the aircraft's design and demonstrated its potential for strategic operations against the Japanese mainland. Colonel Carl immediately began planning additional missions, including strikes against shipping in Japanese ports and attacks on transportation infrastructure. The 414th Fighter Group received P-47NS in July 1945 and was stationed at North Field on Iwo Jima. The group's commander, Colonel James Johnson, had extensive experience with long-range operations from his previous assignment with the 20th Air Force B-29 program. Johnson understood the strategic implications of the P-47N's capabilities and developed tactics specifically designed to exploit the aircraft's advantages. We could finally take the fight directly to Japan, Johnson wrote in his operational summary. Instead of waiting for Japanese aircraft to attack our bombers, we could seek them out over their own territory and destroy them before they became a threat. The P-47N gave us offensive initiative in the air war over Japan. Johnson's tactical innovations included the use of P-47NS as long-range interceptors, flying standing patrols over Japanese airfields to prevent kamikaze attacks from being launched. These missions, which lasted up to 6 hours, required careful coordination with air-sea rescue forces and precise navigation to ensure aircraft could return to their bases despite changing weather conditions. The group's most successful mission was flown on July 24, 1945, when 12 P-47NS intercepted a formation of 56 Japanese aircraft preparing to attack Allied shipping near Okinawa. The engagement took place over Kyushu at an altitude of 18,000 feet, with the P-47NS using their superior firepower and ammunition capacity to achieve decisive results. Major Thomas Wilson led the attack against the Japanese formation. "We had been airborne for 4 hours when we made contact," Wilson recalled. "Most fighters would have been low on fuel and ammunition by that point. But we still had plenty of both, plus the energy advantage of altitude." The Japanese pilots seemed surprised that American fighters were operating so far from their bases. The engagement resulted in the destruction of 28 Japanese aircraft, including 18 Nakajima Ki-84 fighters and 10 Yokosuka D-4Y dive bombers. The P-47NS suffered no losses, though several aircraft returned to Iwo Jima with battle damage from Japanese defensive fire. The remaining Japanese aircraft abandoned their mission and returned to their bases without attacking Allied shipping. This victory demonstrated the strategic value of the P-47N's long-range capabilities. By maintaining fighter patrols over Japanese airspace, American forces could prevent enemy attacks rather than simply responding to them. The psychological effect on Japanese pilots was significant, as they could no longer count on having unescorted access to their targets. The production challenges facing Republic Aviation during P-47N manufacturing were immense. The aircraft required specialized tooling, precision fuel system components, and carefully balanced wing assemblies. Each P-47N wing contained multiple fuel cells that had to be leak-proof under the extreme conditions of high-altitude flight. The manufacturing process required coordination between dozens of subcontractors across the United States. Harold Peterson, a production supervisor at the Farmingdale plant, managed the wing assembly line that produced P-47N wings. "We were building the most complex fuel system ever installed in a single-engine fighter," Peterson recalled. Each wing contained multiple fuel cells, transfer pumps, and interconnecting lines. The slightest manufacturing defect could result in fuel leakage or system failure during flight. The wing manufacturing process began with the construction of the basic wing structure, including spars, ribs, and skin panels. Fuel cells were then installed using specialized sealants and attachment methods that could withstand the thermal cycling and pressure differentials encountered during flight. Each fuel system component was individually tested before installation, and the completed wing underwent extensive pressure testing to verify system integrity. Quality control at the wing assembly line was exceptional. Every wing was inspected by at least 3 different quality control inspectors, and any component that failed inspection was immediately removed and replaced. The rejection rate for P-47N wings was approximately 12%, significantly higher than for earlier Thunderbolt variants due to the complexity of the fuel system installation. The engine installation for P-47NS presented additional challenges. The Pratt & Whitney R2877 engine produced 2,800 horsepower, requiring specialized cooling systems and carburetor configurations. Each engine underwent extensive ground testing before installation, including power runs at various altitudes in Republic's high-altitude test cells. Maintenance requirements for the P-47N were significantly more complex than for earlier P-47 variants. Ground crews had to master fuel system servicing procedures, engine maintenance requirements, and electrical system troubleshooting. The aircraft's increased complexity meant that more specialized tools and test equipment were required at forward operating bases. Sergeant William O'Brien, a crew chief with the 413th Fighter Group, was responsible for maintaining 4 P-47N aircraft. "These airplanes required constant attention," O'Brien recalled. "The fuel system alone had dozens of components that could fail. We had to check fuel pump operations, transfer valve settings, and fuel quantity indicators before every flight. A single malfunctioning component could abort a mission or endanger the pilot's life." O'Brien's maintenance logs documented the extensive servicing required between missions. Each P-47N required approximately 16 hours of maintenance for every hour of flight time, compared to 12 hours for the P-47D. The increased maintenance burden was offset by the aircraft's superior combat capabilities and extended range. The logistics of supporting P-47N operations in the Pacific presented unprecedented challenges. Each aircraft required specialized fuel, ammunition, spare parts, and maintenance equipment. The extended range capabilities meant that missions could last up to 10 hours, requiring precise coordination with weather forecasting, air-sea rescue forces, and base operations. Lieutenant Colonel David Shaw served as the operations officer for the 414th Fighter Group on Iwo Jima. Shaw's responsibilities included mission planning, fuel calculations, and coordination with higher headquarters. Every P-47N mission was like planning a small invasion, Shaw recalled. We had to coordinate with weather reconnaissance, air-sea rescue, and sometimes the Navy for surface vessel positioning. Shaw's mission planning process began with detailed weather analysis and fuel consumption calculations. Each mission profile was carefully analyzed to determine optimal cruise altitudes, power settings, and fuel transfer procedures. Alternative landing sites were identified in case of emergency, and air-sea rescue forces were positioned along the planned route. The complexity of P-47N mission planning required specialized training for operations staff. Shaw attended a 3-week course at the Army Air Forces School of Applied Tactics, where he learned long-range navigation techniques, fuel planning procedures, and emergency protocols specific to extended over-water operations. Weather forecasting for P-47N missions was critical, as aircraft would be operating at extreme range where alternates might not be available. The 20th Air Force's weather reconnaissance squadrons flew specialized missions to provide detailed forecasts for fighter operations, including wind patterns, cloud cover, and potential storm systems that could affect long-range flights. Major Robert Sterling commanded the Weather Reconnaissance Detachment supporting P-47N operations from Iwo Jima. We were providing forecasts for flights that would last 8 to 10 hours and cover distances up to 2,000 miles, Sterling recalled. A 5-mile-per-hour error in wind speed estimation could mean the difference between an aircraft reaching its destination and running out of fuel over the Pacific Ocean. Sterling's weather teams used a combination of surface observations, upper air soundings, and reconnaissance aircraft data to develop forecasts for long-range fighter missions. The accuracy requirements were extraordinary, as fuel reserves for P-47N missions were calculated to the minimum necessary for safe operations. The psychological challenges faced by P-47N pilots were unique in aviation history. Unlike European operations, where emergency landing fields were available every few hundred miles, Pacific missions involved flights of thousands of miles over open ocean. Pilots had to maintain concentration and navigation accuracy for 8 to 10 hours while knowing that mechanical failure or navigation error could be fatal. Captain Ernest Martinez flew 37 P-47N missions with the 413th Fighter Group. The loneliness was overwhelming, Martinez recalled. You'd be flying for hours over nothing but ocean, knowing that if your engine quit, you had maybe 5 minutes to get into your life raft before the airplane sank. The psychological pressure was intense. Martinez developed a systematic approach to managing the stress of long-range missions. He used a detailed checklist system that provided structure throughout the flight, performed fuel calculations every 15 minutes to monitor consumption rates, and maintained radio contact with other aircraft in the formation to reduce the sense of isolation. The navigation challenges for P-47N pilots were formidable. Missions to Japan involved flights over featureless ocean where traditional landmarks were non-existent. Pilots relied on celestial navigation, radio beacons, and dead reckoning to maintain course accuracy over distances that exceeded the range of most commercial aircraft. Lieutenant James Foster, the navigation specialist for the 414th Fighter Group, developed training programs specifically for long-range P-47N operations. Navigation errors that would be minor inconveniences in Europe became life-threatening emergencies in the Pacific, Foster explained. A 5-degree heading error maintained for 4 hours could put an aircraft 200 miles off course with insufficient fuel to correct. Foster's training program included extensive practice with celestial navigation techniques, radio navigation procedures, and emergency navigation protocols. Pilots learned to use sun angles, star positions, and radio beacon bearings to maintain accurate navigation during extended flights. The training was intense, as navigation errors during combat missions were frequently fatal. The Japanese air defense response to P-47N operations evolved rapidly as commanders recognized the threat posed by the long-range American fighters. Intelligence reports captured after the war revealed sophisticated defensive measures designed specifically to counter extended-range escort missions. Colonel Minoru Genda, commanding officer of the Japanese Army Air Force's Fighter Division, issued tactical instructions to his pilots in June 1945 addressing P-47N operations. The enemy's new long-range fighters can maintain combat operations over the homeland for extended periods, Genda's instructions stated. Our pilots must avoid prolonged engagement with these aircraft and instead focus on quick attacks against the bombers they are escorting. Genda's tactical approach emphasized hit-and-run attacks designed to disrupt bomber formations without engaging the escorting P-47NS in sustained combat. Japanese pilots were instructed to use cloud cover and terrain features to approach bomber formations, make a single high-speed attack pass, and then disengage before the escorts could respond effectively. This defensive strategy had limited success against P-47N escorted bomber formations. The American fighters' extended endurance allowed them to maintain close escort throughout the mission, while their superior firepower and ammunition capacity enabled them to engage multiple targets during a single mission. Major Kenji Yanagiya, a veteran Japanese pilot with the 53rd Sentai, flew several interception missions against P-47N escorted bomber formations. The American fighters were always there, Yanagiya recalled. In the past, we could wait for the escorts to turn back for fuel, then attack the bombers. With the new long-range Thunderbolts, this tactic no longer worked. They stayed with the bombers from takeoff to landing. Yanagiya's combat reports documented the effectiveness of P-47N escort missions. During July and August 1945, Japanese fighter units achieved significantly fewer successful attacks against escorted bomber formations compared to earlier periods when long-range escort was not available. The engineering challenges overcome during P-47N development were remarkable. Republic Aviation's design team, led by Alexander Kartveli, had to solve fundamental problems of fuel storage, weight distribution, and structural integrity while maintaining the performance characteristics that made the Thunderbolt series successful. The wing design process required extensive wind tunnel testing and structural analysis. The addition of fuel cells within the wing structure changed the aircraft's mass distribution and required careful attention to flutter characteristics and structural loading. Each wing was designed to carry up to 93 gallons of fuel while maintaining sufficient strength to withstand combat maneuvering loads. Kartveli's design team used advanced engineering techniques, including finite element analysis and fatigue testing, to ensure the P-47N wing structure could withstand the operational requirements. The wing spars were reinforced with additional material, and the fuel cell attachment points were designed to distribute loads across multiple structural members. The fuel system design was perhaps the most complex aspect of the P-47N development program. The system included multiple fuel cells, transfer pumps, crossfeed valves, and quantity indication systems. Each component had to function reliably under the extreme conditions encountered during high-altitude flight, including temperature variations from -60 degrees Fahrenheit to +140 degrees Fahrenheit. Testing of the P-47N fuel system required thousands of hours of ground testing and flight evaluation. Republic's test pilots flew fuel consumption missions to verify system performance under various operating conditions, including high-altitude cruise, combat maneuvering, and emergency procedures. The fuel system reliability achieved during these tests was exceptional, with failure rates below 1%. The propeller system for the P-47N presented unique challenges due to the aircraft's high power loading and extended operating requirements. The four-bladed Curtiss electric propeller had to provide efficient operation across a wide range of airspeeds and altitudes while maintaining reliability during missions lasting up to 10 hours. Propeller testing was conducted at Republic's flight test facility using specialized instrumentation to measure thrust, efficiency, and vibration characteristics. The propeller blades were balanced to extremely tight tolerances to minimize vibration during extended flights, and the electric pitch change mechanism was designed for high reliability and precise control. The turbo supercharger system used in the P-47N was an evolution of systems developed for earlier Thunderbolt variants, but required modifications to handle the increased operating requirements. The General Electric CH-5 turbo supercharger provided maintained power up to altitudes exceeding 30,000 feet, essential for high-altitude escort missions over Japan. Turbo supercharger development included extensive testing of turbine wheels, wastegates, and intercooler systems. The high temperatures and rotational speeds encountered in turbo supercharger operation required specialized materials and precise manufacturing tolerances. Each turbo supercharger underwent individual testing before installation to ensure performance and reliability standards were met. The avionics systems installed in P-47N aircraft were the most advanced available during World War II. Later production aircraft included tail warning radar, autopilot systems, and improved radio equipment designed for extended range operations. These systems had to function reliably under the challenging conditions encountered during long-range Pacific missions. Radio equipment for P-47N aircraft included high-frequency transceivers capable of maintaining communication over distances exceeding 1,000 miles. The radio systems used advanced antenna designs and signal processing techniques to ensure reliable communication during extended flights over the Pacific Ocean. The radar warning system installed in later P-47N aircraft provided pilots with early warning of approaching enemy aircraft. The system used advanced electronics and signal processing to detect aircraft at ranges up to 20 miles, giving P-47N pilots sufficient time to maneuver for advantageous attack positions. Production scheduling for P-47N aircraft required careful coordination between Republic's engineering, manufacturing, and quality control organizations. The complexity of the aircraft meant that production rates were lower than for earlier Thunderbolt variants, but the strategic importance of the program justified the additional resources required. Manufacturing planning for P-47N production began in early 1944, when Republic's management recognized that Pacific operations would require extended-range fighter capabilities. The production schedule had to account for the time required to develop new manufacturing processes, train workers, and implement quality control procedures specific to the P-47N configuration. Tooling development for P-47N production required the design and manufacture of specialized fixtures, jigs, and assembly equipment. The longer wings and modified fuselage structure meant that existing P-47D tooling could not be used for P-47N production. New tooling had to be designed, manufactured, and tested before production could begin. Worker training for P-47N production was extensive, as the aircraft's increased complexity required specialized skills and knowledge. Republic established training programs for assembly workers, quality control inspectors, and test technicians. The training programs included classroom instruction, hands-on practice, and evaluation procedures to ensure competency levels were maintained. The supply chain management for P-47N production involved coordination with hundreds of suppliers across the United States. Critical components such as engines, propellers, and fuel system elements required careful scheduling to ensure production continuity. Any delay in component delivery could disrupt the entire production schedule. Republic's production control system tracked the progress of each P-47N through the manufacturing process, from initial component fabrication through final delivery. The system provided real-time information on production status, quality metrics, and delivery schedules. This information was used to optimize production efficiency and ensure delivery commitments were met. Quality assurance for P-47N production exceeded standards used for earlier aircraft variants. Each aircraft underwent extensive inspection and testing before delivery, including fuel system pressure tests, engine performance evaluations, and flight testing by Republic's test pilots. The quality standards were necessary given the extreme operating requirements P-47NS would face in Pacific operations. The flight test program for P-47N development was one of the most comprehensive ever conducted for a military aircraft. Republic's test pilots flew thousands of hours evaluating aircraft performance, handling characteristics, and system reliability. The flight test program provided the data necessary to validate design decisions and ensure operational safety. Captain Howard Davis, Republic's chief test pilot, flew the first P-47N prototype flights during the summer of 1944. The airplane felt different from the first flight, Davis recalled. The longer wings and additional fuel capacity changed the handling characteristics significantly. We had to develop entirely new piloting techniques for fuel management and long-range navigation. Davis's test flights included evaluation of fuel system operation, engine performance, and flight handling characteristics across the entire operational envelope. The test program revealed several areas requiring design modification, including fuel transfer procedures, engine cooling, and control system response. The fuel system evaluation flights were particularly challenging, as they required flights lasting up to 10 hours to verify fuel consumption rates and system reliability. Davis and his team flew fuel exhaustion tests to determine actual range capabilities under various operating conditions. These tests provided the data necessary for operational fuel planning and mission scheduling. Engine testing during the P-47N flight test program verified the reliability of the Pratt & Whitney R-2877 power plant under extended operating conditions. The engines were operated at various power settings for durations exceeding those encountered during typical combat missions. The testing revealed excellent reliability characteristics, with engine failure rates well below acceptable limits. Handling characteristics evaluation included testing of flight controls, stability, and maneuvering performance across the P-47N's operational envelope. The longer wings and modified fuel system changed the aircraft's center of gravity range and required careful evaluation to ensure safe handling characteristics under all loading conditions. The weapons system evaluation for P-47N aircraft included testing of the .850 caliber machine gun installation, ammunition feed systems, and gun sight accuracy. Each weapon system component was tested individually and as part of the integrated system to ensure reliable operation under combat conditions. Ammunition testing included evaluation of various .50 caliber cartridge types, including armor-piercing, high-explosive, and incendiary rounds. The testing determined optimal ammunition loadouts for various mission types and provided data on gun barrel life and maintenance requirements. The gun sight system installed in P-47N aircraft used advanced optical technology to provide accurate aiming information under various flight conditions. The sight system included gyroscopic stabilization and ballistic computing capabilities that improved accuracy during air-to-air and air-to-ground engagements. Environmental testing of P-47N systems included evaluation of performance under extreme temperature, humidity, and altitude conditions encountered during Pacific operations. The testing ensured that all systems would function reliably under the challenging environmental conditions encountered during combat missions. High-altitude testing was conducted using specialized test facilities that simulated conditions up to 40,000 feet altitude. The testing verified that fuel systems, engine accessories, and avionics systems would function properly under low pressure and low temperature conditions encountered during high-altitude flight. Tropical environmental testing evaluated P-47N systems under high temperature and humidity conditions typical of Pacific operating bases. The testing identified potential corrosion problems and led to the implementation of improved protective coatings and maintenance procedures. The logistics support system developed for P-47N operations was unprecedented in scale and complexity. The extended range capabilities of the aircraft required fuel supplies, spare parts, and maintenance equipment to be positioned at forward operating bases throughout the Pacific theater. The logistics planning had to account for the unique requirements of extended range fighter operations. Fuel logistics for P-47N operations required the positioning of high-octane aviation fuel at bases throughout the Pacific. Each P-47N consumed approximately 800 to 1,000 gallons of fuel per mission, requiring careful planning to ensure adequate supplies were available. The fuel had to be transported by ship or aircraft to forward bases with limited storage capacity. Colonel Robert Hayes commanded the logistics support group responsible for P-47N operations in the Pacific. "We were supporting fighter missions with ranges exceeding those of most bombers," Hayes recalled. The fuel requirements alone were staggering. Each P-47N group required approximately 20,000 gallons of fuel per day during active operations, Hayes's logistics organization coordinated fuel deliveries, spare parts distribution, and maintenance support for P-47N units throughout the Pacific Theater. The organization used advanced planning techniques and transportation optimization to ensure mission readiness was maintained despite the challenging logistics environment. Spare parts management for P-47N operations required sophisticated inventory control systems and rapid transportation capabilities. The complexity of the aircraft meant that hundreds of different spare parts were required to maintain operational readiness. Critical components had to be available at forward bases within hours of failure. The maintenance support system for P-47N operations included specialized tools, test equipment, and technical personnel trained in the aircraft's complex systems. Mobile maintenance units were developed to provide support at forward operating bases that lacked permanent facilities. Transportation of P-47N aircraft to Pacific operating bases required the use of escort carriers and specialized shipping procedures. The aircraft were partially disassembled for shipment, then reassembled and test-flown at their destination bases. The transportation process required careful coordination to ensure aircraft arrived in operational condition. The escort carrier USS Manila Bay transported P-47N aircraft to Saipan during spring 1945. The carrier's deck was modified with specialized equipment for securing and protecting the aircraft during the trans-Pacific voyage. Weather conditions during the voyage were challenging, with several severe storms testing the aircraft's securing systems. Commander Frank Wilson commanded the Manila Bay during P-47N transport missions. "We were carrying the most advanced fighter aircraft in the world," Wilson recalled. "The responsibility was enormous. Any damage during transport could delay combat operations and potentially affect the outcome of critical missions." Wilson's ship transported 120 P-47N aircraft during 6 voyages between March and July 1945. The transport operations required precise coordination with loading, securing, and unloading procedures developed specifically for P-47N aircraft. Weather forecasting for escort carrier operations required detailed analysis of Pacific storm patterns and sea conditions. The carriers had to avoid severe weather systems that could damage aircraft or threaten the ship's safety. Alternative routes were planned to minimize weather exposure while maintaining delivery schedules. The combat effectiveness of P-47N aircraft was demonstrated repeatedly during the final months of World War II. The aircraft's extended range and heavy firepower provided American forces with unprecedented air superiority over Japanese territory. The strategic impact of P-47N operations extended far beyond the number of enemy aircraft destroyed. Statistical analysis of P-47N combat operations revealed exceptional performance metrics. The aircraft achieved an air-to-air kill ratio of approximately 8-to-1 during combat operations over Japan. The loss rate for P-47N aircraft was less than 1% per mission, significantly lower than rates achieved by other fighter types operating in the Pacific Theater. Major General Curtis LeMay, commanding the 21st Bomber Command, recognized the strategic value of P-47N escort operations. "The long-range Thunderbolts transformed our bombing campaign," LeMay wrote in his post-war analysis. "For the first time, we could provide continuous fighter escort for missions anywhere in Japan." The psychological effect on Japanese pilots was as important as the physical protection provided to our bombers. LeMay's bomber formations achieved significantly lower loss rates when escorted by P-47N aircraft compared to unescorted missions. The presence of long-range escort fighters forced Japanese air defense commanders to modify their tactics and reduced the effectiveness of interceptor attacks against American bomber formations. Intelligence analysis of Japanese documents captured after the war revealed the impact of P-47N operations on enemy morale and tactics. Japanese pilots reported feeling overwhelmed by the presence of American fighters that could maintain combat operations for extended periods without refueling. Lieutenant Colonel Hiroshi Tanaka, a Japanese air defense analyst, wrote in his post-war memoir, "The American P-47N aircraft changed the entire character of the air war over Japan. We could no longer predict when and where American fighters would appear. Their range capabilities meant that nowhere in Japan was safe from fighter attack." Tanaka's analysis documented the disruption of Japanese training operations, aircraft production, and pilot replacement programs caused by P-47N fighter sweeps over the homeland. The constant threat of American fighter attack forced Japanese forces to disperse aircraft and reduce flying activity, significantly degrading combat readiness. The technological legacy of the P-47N development program extended far beyond World War II applications. The engineering solutions developed for extended-range fighter operations influenced post-war aircraft design and established principles that remain relevant in modern aviation. Fuel system technology developed for the P-47N influenced the design of subsequent military and civilian aircraft. The techniques for integrating fuel storage within wing structures, managing complex fuel transfer systems, and maintaining system reliability during extended operations became standard practices in aircraft design. Dr. Alexander Kartveli continued to apply lessons learned from P-47N development in his subsequent aircraft designs. The Republic F-84 Thunderjet and F-105 Thunderchief incorporated fuel system concepts and structural techniques originally developed for the P-47N program. Manufacturing processes developed during P-47N production influenced post-war aircraft manufacturing methods. The quality control procedures, production planning techniques, and worker training programs established during P-47N production became models for subsequent aircraft manufacturing programs. The operational techniques developed for P-47N missions established principles for long-range fighter operations that remained relevant throughout the jet age. Fuel planning procedures, navigation techniques, and mission coordination methods developed during P-47N operations influenced Air Force doctrine for decades after World War II. Training programs developed for P-47N pilots emphasized skills and knowledge that became essential for jet aircraft operations. The emphasis on fuel management, navigation accuracy, and systems management prepared pilots for the increased complexity of post-war aircraft. Post-war analysis of P-47N combat operations provided valuable data for aircraft designers and military planners. The performance data collected during combat missions validated design concepts and operational techniques that influenced subsequent aircraft development programs. The strategic impact of P-47N operations during World War II demonstrated the importance of extended-range fighter capabilities in modern warfare. The ability to project air power over vast distances became a cornerstone of post-war military aviation doctrine. Air Force planners recognized that future conflicts would require fighter aircraft with capabilities similar to those demonstrated by the P-47N. The requirement for extended range, heavy armament, and robust construction became standard specifications for subsequent fighter aircraft development programs. International recognition of P-47N capabilities influenced aircraft development programs in other countries. The success of American long-range fighter operations demonstrated the strategic value of such capabilities and encouraged similar development programs in allied and neutral nations. The industrial base established for P-47N production provided the foundation for post-war aircraft manufacturing capability. The skilled workforce, manufacturing facilities, and supply chain relationships developed during P-47N production supported continued aircraft development and production after the war. Republic Aviation's experience with P-47N development and production established the company as a leader in fighter aircraft design and manufacturing. The technical expertise and manufacturing capability developed during the program positioned Republic for continued success in the jet age. The P-47N program demonstrated the importance of government-industry partnership in developing advanced military systems. The cooperation between Republic Aviation, the Army Air Forces, and numerous subcontractors established models for subsequent aircraft development programs. Quality control standards established during P-47N production influenced aircraft manufacturing quality requirements for decades after World War II. The emphasis on reliability, performance, and safety became standard expectations for military aircraft production. Research and development methods used during P-47N development established principles for managing complex aircraft development programs. The systematic approach to testing, evaluation, and design modification became standard practice for subsequent aircraft development efforts. The P-47N program's success demonstrated the value of investing in advanced aircraft capabilities during wartime. The strategic advantages provided by superior aircraft justified the resources required for development and production, establishing precedents for future aircraft investment decisions. Environmental testing techniques developed during P-47N evaluation became standard practices for aircraft development programs. The comprehensive evaluation of aircraft performance under extreme operating conditions ensured operational reliability and safety. System integration methods used in P-47N development established principles for managing complex aircraft systems. The techniques for integrating engines, fuel systems, avionics, and weapons systems became models for subsequent aircraft design efforts. The human factors considerations addressed during P-47N development influenced aircraft cockpit design and pilot training for decades after World War II. The emphasis on pilot workload, situational awareness, and system management became standard elements of aircraft design. Logistic support concepts developed for P-47N operations established principles for supporting advanced military systems in remote locations. The techniques for fuel supply, parts distribution, and maintenance support influenced military logistics planning for decades. Training system development for P-47N operations demonstrated the importance of comprehensive pilot and maintainer education programs. The systematic approach to skills development and knowledge transfer became models for subsequent military training programs. The economic impact of P-47N production extended far beyond the immediate wartime requirements. The program employed thousands of workers, stimulated technological development, and established industrial capabilities that continued to benefit the economy after the war. Regional economic development resulting from P-47N production created lasting benefits for communities surrounding Republic's manufacturing facilities. The skilled workforce and industrial infrastructure developed during the program supported continued economic growth in these regions. Technological spillover effects from P-47N development influenced civilian aviation, automotive, and industrial applications. The engineering techniques, material science, and manufacturing processes developed during the program found applications in numerous civilian industries. The educational impact of P-47N development included the training of engineers, technicians, and managers who continued to contribute to American industrial development after the war. The skills and knowledge developed during the program became part of the nation's technical expertise base. International technology transfer resulting from P-47N operations influenced aircraft development in allied nations. The sharing of design concepts, manufacturing techniques, and operational procedures strengthened allied industrial capabilities and military effectiveness. Research facilities and capabilities developed during P-47N testing continued to support aircraft development after World War II. The wind tunnels, test equipment, and measurement techniques established during the program provided infrastructure for continued aerospace research. The documentation and analysis of P-47N development and operations created a knowledge base that influenced aircraft design and military planning for decades. The technical reports, operational analyses, and lessons learned became reference materials for subsequent programs. Safety improvements developed during P-47N operations established principles for aircraft safety that remain relevant in modern aviation. The emphasis on redundant systems, emergency procedures, and pilot training became standard elements of aircraft safety programs. Performance standards established during P-47N development influenced aircraft specification requirements for decades after World War II. The emphasis on reliability, maintainability, and operational effectiveness became standard expectations for military aircraft. The cultural impact of P-47N operations extended beyond military aviation to influence American perceptions of technological capability and industrial achievement. The success of the program demonstrated American ability to develop and produce advanced military systems under wartime pressures. Public awareness of P-47N capabilities contributed to American confidence in technological solutions to military challenges. The aircraft's success demonstrated the value of investing in research, development, and advanced manufacturing capabilities. Media coverage of P-47N operations influenced public understanding of air warfare and technological development. The stories of long-range missions over the Pacific captured public imagination and demonstrated the strategic importance of air power. Veterans of P-47N operations carried their experiences into post-war careers in aviation, engineering, and business. Their knowledge and expertise contributed to American technological and economic development during the post-war period. The organizational innovations developed during P-47N production influenced business management practices in numerous industries. The techniques for project management, quality control, and workforce development became models for industrial organization. International cooperation during P-47N operations strengthened relationships between the United States and allied nations. The shared experience of developing and operating advanced military systems contributed to continuing cooperation in defense and technology areas. The P-47N Thunderbolt represented the culmination of American fighter aircraft development during World War II. Its combination of range, firepower, and reliability provided capabilities that transformed air warfare in the Pacific theater and established principles that continue to influence military aviation. On August 15, 1945, Emperor Hirohito announced Japan's surrender, ending World War II. The P-47N aircraft that had been preparing for the invasion of Japan were no longer needed for their original purpose, but their impact on military aviation would continue for decades. The final P-47N rolled off Republic's production line in October 1945, ending one of the most successful fighter aircraft programs in history. The aircraft that had been designed to escort bombers to Japan had proven that American technology and industrial capability could meet any challenge presented by wartime requirements. Lieutenant Urban Drew, who had flown that final mission over Japan on August 14th, survived the war and returned to civilian life. His P-47N, Detroit Miss-2, was eventually scrapped along with thousands of other military aircraft no longer needed for peacetime operations. But the technological advances and operational concepts developed during the P-47N program continued to influence aviation development for generations. The men and women who designed, built, and flew the P-47N Thunderbolt had created more than just an airplane. They had developed capabilities that demonstrated American technological superiority and industrial strength. The lessons learned during the P-47N program became part of the foundation for American aerospace leadership that continues to this day. The strategic impact of P-47N operations during World War II extended far beyond the aircraft's immediate military contributions. The program demonstrated American ability to identify military requirements, develop technological solutions, and implement them effectively under wartime pressures. These capabilities became central elements of American defense strategy during the Cold War and beyond. Today, as military planners consider the requirements for future conflicts, they continue to reference lessons learned from programs like the P-47N. The need for long-range, heavily armed fighter aircraft remains relevant in an era of global military operations and emerging threats. The P-47N Thunderbolt stands as a testament to American engineering excellence, industrial capability, and military effectiveness. Its development and operation during World War II demonstrated that superior technology, combined with skilled personnel and effective organization, could achieve decisive military advantages. The legacy of the P-47N extends beyond military aviation to encompass broader themes of technological innovation, industrial achievement, and national capability. The program showed that American industry could meet any challenge and produce systems that exceeded the capabilities of potential adversaries. In the end, the P-47N Thunderbolt was more than just a fighter aircraft. It was a symbol of American technological superiority and industrial strength that helped secure victory in World War II and establish precedents for continued aerospace leadership in the post-war era. The story of the P-47N reminds us that technological advantage in military affairs requires sustained investment in research, development, and industrial capability. The lessons learned from this remarkable aircraft continue to inform American defense planning and aerospace development as we face the challenges of the 21st century. As we reflect on the achievements of the P-47N program, we honor not only the aircraft itself but also the thousands of engineers, workers, and aircrew who made its success possible. Their dedication and expertise created capabilities that helped secure American victory in the Pacific and established foundations for continued aerospace leadership. The P-47N Thunderbolt flew its final combat missions in August 1945, but its influence on military aviation continues today. Every time a modern fighter aircraft performs a long-range mission, conducts extended operations over hostile territory, or demonstrates superior technological capability, It carries forward the legacy of the Thunderbolt that could fly 2,350 miles and changed the course of history.